Hello Chemistry 30 and welcome to your video on Ka expressions and values. What this is it's a tool to figure out stuff for weak acids. Everything we've done so far has been for strong acids or for strong bases, but now we're focusing in on actually weak acids and weak bases on how to calculate hydronium or hydroxide or the acid concentration when you have other information. So today's objective is to calculate equilibrium constants and concentrations for homogeneous systems and Bronsted-Lowry acids and bases. So let's get into it here. So Ka is the constant that is the acid ionization constant. So for a general equilibrium, we've done Kc. Now what we're doing instead is Ka, which is just for any general acid, the equilibrium constant once I build the expression. And what you're going to learn is that we actually have a acid ionization formula. Like we can get a formula for Ka that enables us to basically figure it out quite easily for a weak acid. So let's say that we had this equilibrium, HF and water making hydronium and the fluoride ion. So here HF is obviously the acid, water is acting as a Bronsted-Lowry base because it accepts a proton to make hydronium, and then this is my conjugate base over here. So how would I write the equilibrium expression for this equation? So let's go ahead and just actually say, hey, this is Ka. Well, we would have products of hydronium and then we had fluoride ion, F minus, as a product, over HF. We don't include the water because, of course, it is a liquid, so therefore it is not included in our Bronsted-Lowry, or our equilibrium expression, sorry. So we're not going to include that at all. So now that I have that Ka expression, let's now try to figure a little bit more out. And basically what I can say here is that we can simplify this a bit. We're going to get back to that, I think, in just a moment. Ka values are in our data booklet. They're on the right-hand side here. So for oxalic acid, for example, it's 5.6 times 10 to the negative 2. So we have Ka values given to us in our data booklet, just ready to go for us to use. So we're going to use these Ka values quite a bit throughout this kind of lesson and then going into your work for today. You'll notice that as I go down, the values are getting less and less and less. So this is my strongest weak acid, which has a value of 0.056, right, for my Ka value. Hydronium is a 1, and then over here we have very large, right? So essentially just we don't have a value for it, but it's essentially quantitative in how it reacts. Okay, so going back to this, if there was no F minus or hydronium present before HF was added, what can be said about hydronium and fluoride? So essentially I don't have any of this to start out, right, before it was added. And if we assume that there was no hydronium to begin with, which isn't completely true, but it's pretty close to true, because to begin with in a normal solution, it would be 1.0 times 10 to the negative 7 if it was neutral distilled water, right? So given that, it's very, very incredibly low. What I could say is that essentially for hydronium and fluoride, hydronium is approximately equal to fluoride, F minus aqueous, right, for concentration. We can say that these are pretty much the exact same concentration at equilibrium. The other thing we can say is that because weak acids ionize so little compared to like a strong acid or just period, very little of this HF reacts to this, that if we just know the concentration of the original HF, that's essentially equal to or very close to the F minus, or sorry, the initial is very close to the equilibrium HF concentration. So we can also say that HF, don't know why I wrote it that way, HF initial is approximately equal to HF final. And again, that's because for weak acids, so little of it actually ionizes, okay, such a little amount that it really doesn't matter that much. And this is an assumption that makes our work incredibly Easy. So these are two assumptions we are making in the formula I'm going to tell you right now. And that formula is that Ka is equal to hydronium squared over HF. Where this is just like my initial or just concentration of HF as it's told in the question. Okay, so what I did is just said, well, this and this is equal, right? It's pretty much the same, approximately equal, I should say. It's pretty much the same. So let's just combine it under hydronium squared. And then HF, whatever concentration I have for HF, it's going to be pretty much the same at equilibrium as it was initially because so little of this turns into these that we're just going to say whatever concentration I have for HF, that's the concentration. I'm plugging it in, and I'm not going to do like minus X stuff in order to find the equilibrium concentration of HF. I'm just going to take the initial concentration of HF and treat that as the same. Now, this gives us a very, very easy to use formula for weak acids that gets pretty good results. Do these assumptions cause errors? Yeah, it does, like a little tiny, tiny error. But for almost all acids, that error is so small that with significant digits, it doesn't actually change the answer at all. Or if it does, it's not important. It's such a small amount that using this method gives us a very good approximation for hydronium concentration or Ka or whatever we're finding, that it's fine. It works out well by making these assumptions. So are these things true? Is this truth that hydronium is equal to fluoride at equilibrium? No, not quite. Really close, but not quite. And is this true that HF initial is equal to HF final? No, that's not true, but it's pretty close. So if we just treat that way, then we can make the this formula that gets us a pretty decent answer very, very simply. Without having to use ice charts and stuff, it gets us values that are very, very good. So let's take a look at an example and see how this pans out. So this one is calculating a Ka, so I have a 0.15 mole per liter solution of a weak acid. Normally for a weak acid, when it's unknown, we don't actually know where any acid when it's unknown and we don't have a formula for it. We just call it HA, meaning that H is our proton, of course, right? And then we just have A kind of for acid. It has a pH of 5.00, calculate the Ka for the acid and write the chemical equation. So I know that hydronium concentration based on my pH is equal to 10 to the negative pH, right? So I got 10 to the negative 5.00. So in other words, I have 1.0 times 10 to the negative 5 moles per liter in significant digits. So that means that my Ka is equal to hydronium squared over HA, my acid concentration. So I have 1.0 times 10 to the negative 5 squared over my acid concentration of 0.15. So let's plug this in and see how we make out on this. So let's go ahead and put in 1.0 second E negative 5. Oh, that's not a negative, that's a minus. That would be a problem. We're going to square that. And then we're going to divide that by 0.15. And I get a value of Ka is equal to 6.7 times 10 to the negative 10 for a Ka value. So now if I actually just go back and take a look at this page where I'm looking at different values, I would know that this is way down below. And if I look at maybe lower in the data booklet, I think I got a screen later on here that shows me the bottom kind of portion of this. Here we go. It'd be somewhere just above hydrocyanic acid, right? 6.7 times 10 to the negative 10. That's where hydrocyanic acid is. So it'd be just a little bit above this before hypochlorous acid. So it is kind of interesting to see where that value relates to how strong of an acid it is. And this is a fairly weak acid. All right, so that's a Ka calculation. Let's now try something where we're finding, let's say, hydronium. So calculate the hydronium ion concentration and pH of a 0.10 mole per liter solution of nitrous acid. All right, so I'm trying to find hydronium. I have a concentration of an acid, and I also can look at, for nitrous acid, what the Ka value actually is. And I kind of messed up here that I did not snag that value for nitrous acid. Maybe it's over on this page, hopefully. No, it is not. I don't have nitrous on there. Oh, what a mess. So bear with me while I open up my data booklet so we can take a look at this. And maybe this is a good exercise to show you exactly where we would find this. So if I go to my data booklet, and here it is, I'm going to have to now change the view so it's the right way. Give me 1 second here. Oh, what a mess. All right, rotate view clockwise. Awesome. Bring back that page down until we get to this nitrous, right, here we go, HNO2, and that's 5.6 times 10 to the negative 4 for a Ka value. So I've got that set up. So 5.6 times 10 to the negative 4. So Ka is equal to hydronium squared over my acid concentration of HA. So I'm trying to find hydronium, so I'm going to have to take HA and put it over here. So I have HA, oh, did the A wrong, I'm thinking Ka. HA times Ka is equal to hydronium squared. So now if I want hydronium, I'm just going to take the square root of both sides. So square root of HA and Ka. So square root of 0.10, and that 5.6 times 10 to the negative 4. So really what I'm doing here is 5.6 times 10 to the negative 5 and taking the square root of that. But let's go through the full motions. Square root 0.10 times 5.6 second e negative 4. Close that, and I end up with 0.0075 moles per liter as an answer to my hydronium concentration. So now if I wanted to find the pH of that, I would just do negative log of my hydronium, H3O positive. So I have negative log of 0.0075 moles per liter. So negative log of that is going to get me 2.13 for a pH. 2.13. So I mean fairly acidic, right? That's a fairly acidic solution. And this was 0.10 moles per liter. So I mean, it's a pretty high concentration of nitrous acid. All right, so that's a Ka calculation. That covers it. We did a Ka calculation, we did a hydronium and a pH calculation. It's really quite simple for these weak acids. And using this formula, this simplified formula, okay, it makes things quite a lot easier than we would have had otherwise if we had to build an ice chart and work it out. So this is the better way to go by far for finding it in terms of simplicity, by making the assumptions, like I said, that hydronium concentration is the same as the conjugate base concentration, and also that whatever concentration I have the acid, that the initial and the equilibrium are essentially the same, because so little of a weak acid actually ends up ionizing or reacting with water to make hydronium. Okay, that's it for Ka. Have a good rest of your day.